The parallelization of algorithm based on horizontal partition for association rule mining on large data set. Abstract data mining can abstract important facts such as frequent item set from large data set, but sometimes it is difficult to achieve all frequent item set if these datasets are split into many clusters when there is a large data set. In this paper, a detailed comparison has been made for the frequent pattern mining algorithms such as Apriori, ECLAT, and FP Growth based on without partitioning and with horizontal partitioning of dataset by applying actual minimum support as well as with dynamic minimum support. Experimental results shows that after partitioning also we can maintain similar accuracy and have obtained 100% frequent item set in contrast with frequent item set achieved without partitioning. This novel concept is useful to search frequent item set from the large dataset when we applied the concept of partitioning. It also shows that till which extent minimum support should be decreased with respect to number of cluster to achieve maximum accuracy or 100% frequent item set. Keywords: association rule mining, frequent items data set, Apriori algorithm, ECLAT, FP growth, minimum support, parallel computing. Introduction. Data mining is concentrate on discovering interesting hidden relationships in large databases. It provides a tool for knowledge discovery to extract unknown and potentially interesting knowledge from data set 1. One amongst the important techniques utilized in DM is association rules. Association rule is employed to find interesting patterns among large set of knowledge items, which is an important task of information mining 2. 3. Finding frequent item sets in transaction databases has been proven to be useful in retail business applications 611. Many algorithms are proposed to hunt out frequent item sets from a very large database. However, there is no published implementation that outperforms every other implementation on every database with every different support 7. Generally, many implementations are supported these main algorithms, Apriori 2, frequent pattern growth, FP growth, 4 and ECLAT. The Apriori algorithm discovers the frequent item sets from an awfully large database through a series of iterations. The Apriori algorithm is required to huge candidate item sets, compute the support, and prune the candidate item sets to the frequent item sets in each iteration. The FP growth algorithm discovers frequent item sets with less the time. The Apriori algorithm has been looked over in numerous ways. One review of the Apriori algorithm is to partition a transaction database into divide partitions DB1, DB2, DB3, DBN. Partitioning a transaction database may improve the performance of frequent item sets mining by adjust each partition into main memory for fast access and allowing incremental generation of frequent item sets. Our implementation is a partition whole dataset in different number of clusters horizontally and generate frequent item set using Apriori algorithm, FP_growth, and ECLAT using parallel computing. It observed that once large dataset partition into many cluster then it lost many important frequent item set because of many reason like customer buying pattern, sessional product requirement, seller discount offer etc. Although many algorithms have been proposed, the execution accuracy of frequent pattern mining is still a challenge to the researchers due to the data outburst. Later section of this paper we will see efficient parallel computing approach using dynamic minimum support. The rest of this paper is organized as follows. Related work is presented in section 2. Proposed methodology is presented in section 3. Results and discussion are presented in section 4. Conclusions and future work are discussed in section V. 2. Literature review. In order to improve the performance of association rule mining, many researchers tried to distribute dataset into the mining computation over more than one processor or a traditional computer have multi-core for executing a task. One way of increasing the computational speed is by using all core within a single computer. The most famous is the Apriori algorithm which has been brought in 1993 by Agrawal et al. Which uses association rule mining 2 3 5 6 8 9 10. Association rules are usually required to satisfy a user-specified minimum support and a user-specified minimum confidence at the same time. Association rule generation is usually split up into two separate steps. One minimum support, threshold, is applied to find all frequent item sets in a database. 2. These frequent item sets and the minimum confidence constraints are used to form rules. Advantage of this algorithm, it is easy to find frequent item sets if database is small. But it has two deadly bottlenecks. First, it needs great I/O load when frequently scans database, and second, it may produce overfull candidates of frequent item sets. Another accomplishment in the development of association rule mining and frequent pattern mining is FP growth algorithm which overcomes the two deficiencies of the Apriori algorithm. Efficiency of FP growth is based on three salient features. A divide and conquer approach is used to extract small patterns by decomposing the mining problem into a set of smaller problems in conditional databases, which consequently reduces the search space. 2. FP growth algorithm avoid the complex candidate item set generation process for a large number of candidate item sets. And 3. To avoid expensive and repetitive database scan, database is compressed in a highly summarized, much smaller data structure called FP tree. 4. Equivalence class clustering and bottom-up lattice traversal, ECLAT. 7. With vertical data format uses intersection of transaction IDs list for generating candidate item set. Each item is stored with its list of transaction IDs instead of mentioning transaction IDs with list of items. This algorithm uses breadth first search, BFS, and the generation of candidate item set is needed. Equivalence class clustering and bottom-up lattice traversal, ECLAT. Algorithm accommodates depth first search approach and requires the generation of candidate item set. Proposed a system to reduce the general items and items to be assembled and consequently improve sales in supermarkets. The approach is particularly suitable for analyzing customer performance in relation to purchases of goods and improving the point of sale in supermarkets. An example is customer buying habits that use the Belgian shopping market database, where purchase data, prices, and price are used to determine customer behavior and display related information to support sales. In results, it has been shown that the time and memory required for the generation of raw materials is reduced by the generation of well-made rules. 11. Develop a system which proposed for frequent item set mining, where author developed parallel analytical model by integrating R on Hadoop. 12. It shows that as the frequent item set is important for inference engine and for analysis, it is important to resolve the problems which arise from large data set. The proposed system takes data into a pre-processing optimizer and it runs it on multistage algorithm. It uses MapReduce application along with some association rules. It showed that a same list is used for operations of MapReduce and is handled with multiple algorithms to give minimized output. One of the drawbacks can be that it doesn't support cyclic flow of data or incremental data. Proposed inverted matrix, which is a new disk-based parallel association rule mining with minimum interprocessor communication. 13. Apriori algorithm, which works on a shared nothing algorithm, is not scalable. The inverted matrix has two phases where a global frequent pattern is achieved where the transactional dataset is converted into inverted matrix. The dataset is replicated among many parallel nodes using different support level of association rules. By doing so, a global frequent pattern can be generated without communication between node and the load is balanced. The inverted matrix combines both horizontal layout and vertical layout and makes the best of both the approaches. The inverted matrix is based on COFI trace. The results of this algorithm acquired 8 nodes with 16 clusters. The paper proposes that we need to have embarrassingly parallel algorithms to store massive side and also to allow random access, and also to allow no communication between nodes. Emphasized on the importance of finding frequent item set of large data set. One of the most effective algorithm to find frequent item set is the a priori, which trims the candidate item set and also finds the support. Hash trace is used in a priori algorithm. The focus of this paper is based on implementing Apriori algorithm using tree structure and analyze its performance of parallel processor. Partitioning helps in quick access and allows the item sets to be generated incrementally. Tree structure is an effective way to store item set and to access them. A tree gets created incrementally based on the count of item set. This implementation solved most of the problems of frequent mining faster than most of the implementations, but had an issue in load balancing. 14. KW Lin and Y Luo propose a plan to find fast frequent item set in cloud computing by utilizing cloud nodes and also prevent the data from getting leaked. The data getting leaked becomes an issue because when we divide the data set and each processor is distributed with a part to mine, there is an exchange among nodes which increases the load and the database is duplicated to every node. This framework has a kernel cloud which can access the database and has all the information related to the available nodes. As the FP tree stores data in compressed form as compared to a priori algorithm. 3. Proposed methodology. It is difficult to generate frequent item set from large data set in any existing algorithms because existing algorithms create large candidate set, hence it's impossible to fit into primary memory. This issue can be resolved with the help of parallel computing concept. Divide dataset into many clusters so that it is easy for CPU to generate FIS and it will not face any issue related to memory. Problem identified. As we know, when dataset divides into many clusters or partition the dataset, it will lost many FIS in process of partition processing. Hence, We proposed a concept dynamic minimum support where it will decrease the minimum support up to certain limit with respect to number of cluster and actual minimum support, and next section will show with the help of dynamic support we can achieve almost similar support that we achieved without clustering. Fig 1 shows the deviation of dynamic minimum support over static minimum support with increase in no of clusters. Dynamic min support is calculated as dynamic min support equals actual min support / log. It indicates the logarithmic decrease in dynamic minimum support in order to achieve higher accuracy of FIS in contrast to lower accuracy of FIS with static minimum support over clustering for horizontal approach. The table 2 shows execution time comparison of normal approach, without clustering, w.r.t horizontal approach, with dynamic / static min support and clustering, for a priori algorithm over 1 log to 10 log transaction with minimum support equals 0.01 and no of clusters equals 12. Fig 2 shows that a priori algorithms requires much lesser execution time with static min support and in normal approach in contrast with dynamic min support. This is due to much higher no of candidate set generated by a priori algorithm at lower dynamic support value. The table 3 shows the comparison of no of patterns generated in normal approach, without clustering, w.r.t no of patterns generated in horizontal approach, with dynamic / static min support and clustering, for a priori algorithm over 1 log to 10 log transaction with minimum support equals 0.01 and no of clusters equals 12. Fig 3 shows that for a priori algorithm the accuracy of no of patterns generated with dynamic min support is almost equal to 100%, while with static min support it drops to approximate 75 to 85% in contrast with no of patterns generated in normal approach, without clustering. The table 4 shows execution time comparison of normal approach, without clustering, w.r.t horizontal approach, with dynamic / static min support and clustering, for FP growth algorithm over 1 log to 10 log transaction with minimum support equals 0.01 and no of clusters equals 12. Static min support and clustering, in contrast with normal approach. This is due to clustering, which results into smaller tree structures in horizontal approach with lesser branching factor. The table 5 shows the comparison of no of patterns generated in normal approach, without clustering, w.r.t no of patterns generated in horizontal approach, with dynamic / static min support and clustering, for FP growth algorithm over 1 log to 10 log transaction with minimum support equals 0.01 and no of clusters equals 12. Fig 5 shows that for FP growth algorithm the accuracy of no of patterns generated with dynamic min support is around 85%, while with static min support it drops to approximate 75% in contrast with no of patterns generated in normal approach, without clustering. Table 6, execution time required by ECLAT algorithm with clustering, dynamic / static min support, and without clustering. The table 6 shows execution time comparison of normal approach, without clustering, w.r.t horizontal approach, with dynamic / static min support and clustering, for ECLAT algorithm over 1 log to 10 log transaction with minimum support equals 0.01 and no of clusters equals 12. Fig 6 shows that ECLAT algorithms requires a bit lesser execution time in horizontal approach with dynamic / static min support using clustering in contrast with normal approach. The table 7 shows the comparison of no of patterns generated in normal approach, without clustering, w.r.t no of patterns generated in horizontal approach, with dynamic / static min support and clustering, for ECLAT algorithm over 1 log to 10 log transaction with minimum support equals 0.01 and no of clusters equals 12. Fig. 7 shows that for ECLAT algorithm the accuracy of no of patterns generated with dynamic min support is almost equal to 100%, while with static min support it drops to approximate 75 to 85% in contrast with no of patterns generated in normal approach, without clustering. Conclusion. It conclude that in all above algorithms accuracy, FIS, sustained by dynamic min support is almost equal to 100%, whereas with static min support it drops to approximate 80% with an increase in no of clusters. In future execution time can be reduced with the help of additional resources, i.e. multiprocessor environment. Also this research can be extended in future to different category of dataset and with more number of transactions.